Okay, so in this video, we will look at the first problem on the problem sheet called related rates. So if you look at this problem sheet, the first part 1 of related rates, this is the first problem. And as you'll see, you'll have very different looking problems, but we will always tackle them in the same way. We'll first try to visualize the situation, then we will label the variables, write down what we know, what we want, then find a relation, that's why it's called related, a relation between the variables, and then we will differentiate because the rate of change, the velocity, is just the derivative. So here's the situation. A stone is thrown in a lake, making a circular wave. Right? Imagine that you have a lake, the water is really calm, and you throw a stone in the lake. Well, the stone will make ripples in the water, and as time goes on, and of course the ripples are circular, and they will get larger and larger and larger. So we're told that the wave is moving at a rate of 0.75 meters per second away from the center, and we're asking how fast is the area inside the wave changing when the wave has a radius of 2 meters. So as always, the first step will be to visualize the situation. So we're throwing a stone in the lake and it makes a circular wave. So imagine this point being the point at which you throw the stone, and it will make circular waves. As time goes on, the wave gets bigger and bigger and bigger. So of course, two things are changing here. The radius of the wave, the initial wave, if we ignore the other ripples, but we only consider the initial wave, so the bigger one, as time goes on, this will get bigger and bigger and bigger, so the radius of our circle is changing. So let's visualize the radius. And every time something is changing, it is a variable, give it a name. Here the radius will change as a function of time. A natural letter for a radius is to use r. So we have our radius. And now, what do we know about the radius? Every time you have a variable, you will be given a rate of change about this variable, how fast is it increasing or decreasing. And you see we're told here the wave, if the wave is moving at a rate of 0.75 meters per second away from the center, that's how fast the radius is changing. But the rate of change is the derivative, right? Suppose that r is measured here in meters. This will be dr, the change in r over the change in time, right? Meters per second, so seconds. So here implicitly we're measuring time in seconds. And we're told that the wave is moving at a rate of 0.75 meters per second away from the center. Therefore, as time goes on, the radius is increasing, so we are going to have a positive rate of change. It will be plus 0.75 meters per second. If over time, say, the radius was decreasing, was getting shorter, then the function r as a function of t would be decreasing, and we would have a negative rate of change. But because over time the wave keeps getting bigger and bigger and bigger, the radius is increasing, therefore it has a positive slope, positive rate of change. And this is all we know, right? This is the only rate of change that we're told. The rate of change of the radius, so the change in the length of the radius over the change in time is 0.75 meters per second. And now, here's the question. This is what we want to find. How fast is the area inside the wave changing? Well, that is another variable, right? As the circle formed by the wave keeps getting bigger and bigger and bigger, the area will also get bigger. And we're asking how fast is the area of the wave changing? Well, again, it's a rate of change. Rate of change is a derivative. Let's call the area uppercase A. And of course, A here is also a function of time. The area changes as time goes on. So this is the derivative of the area with respect to time. And we're asking how fast is the area inside the wave changing, specifically when the wave has a radius of 2 meters. So we want the rate of change of the area exactly when the radius reaches 2 meters. And that's what we want to find. And that's always the first part of any related rate problem. Visualize the situation. If something is changing, give it a variable name, radius area. Write down what you know in terms of the rate of change of certain variables. Write down what you want properly using proper notation of the derivative. And now, the question is, well, where do we go from here? We know the rate of change of the radius. It is a constant rate of change of positive 0.75 meters per second. And we want the rate of change of the area of the circle. And this is when the word related comes in. If you want to know the rate of change of the area, given that you know the rate of change of the radius, you have to relate these two variables together. You have to relate the area of the circle with its radius, and that is the relation. Well, we know the area of a circle is pi r squared. So A is simply pi times the radius squared. And now we have a relation. We have related r with A. And the question is now, once we have the relation, where do we go from here? Well, if you think of it, we are now going to use implicit differentiation. As time changes, r changes, and as time changes, A changes. So, r is a function of time, and the area is also a function of time. And so if you look at the equality, because A is a function of time, the left-hand side is a function of time. Because r is a function of time, the right-hand side is a function of time. So both sides are equal as functions of time, t. Therefore, both sides are equal. Therefore, they have the same derivative with respect to, of course, the independent variable, which here is t. So we just differentiate both sides. So the derivative with respect to t of the left-hand side, which is a, will equal the derivative with respect to t of the right-hand side. Let's differentiate. Well, this is just a, so the derivative of a with respect to t, that's just dA over dt, equals, so we're done with the left-hand side. Well, pi is a real number. It's a constant multiple, right? Approximately 3.1415. Pi being a constant multiple, it will just stay there. So it will be pi times the derivative. And here's where you have to be careful, because we differentiate r squared with respect to t. But r is a function of t, so you have to be careful here by applying the chain rule completely. It is r squared. The outside function is the power 2. By the chain rule, we differentiate the outside function. By the power rule, we bring 2 down. 2 minus 1 is 1. Of what? Of r. But now there's an r left over, times the derivative of r with respect to t, and that's just dr over dt. So what we have in the end will be 2 pi times r. So 2 pi r times dr over dt. But let's go back. We know what dr over dt is. We were told that the rate of change of the radius with respect to time is always 0.75 meters per second. So we can replace dr over dt by 0.75, if you prefer by 3/4. And now let's write our conclusion. Well, almost our conclusion. The rate of change of the area as a function of time will be equal to, well, 2 pi r times 3/4, but 2 over 4, that's just 1/2, so it's 3 over 2 pi times the radius. And finally, we wanted the rate of change of the area, and if you think of it, because r is a function of t, this would be 3 over 2 pi times the radius as a function of time. So what we now have is the rate of change of the area as a function of time, because r is a function of time, but we wanted specifically the rate of change of the area as a function of t when the radius was exactly 2 meters. So we just want to evaluate this function when r equals 2. So let's just evaluate. We want to evaluate the rate of change of the area of the circular wave exactly when r equals 2. Well, this will be 3 over 2 pi times the radius, which we now are setting equal to 2. And if you simplify, you're left with 3 pi. And if you want an approximation, 3 times pi will give you approximately 9.42. And now we can write the units. So when the radius of the wave reaches 2 meters, the rate of change of the area as a function of t, time, will be 9.42. Well, here the units were meters for length, seconds for time. Well, area is meters squared per time, which is second. So when the radius of our wave reaches 2 meters, the rate of change of the area is approximately 9.42 meters squared per second. And if you notice, we have a positive rate of change, which matches the situation. If the rate of change of a quantity is positive, that quantity should be increasing. And it's clear from the problem. As time goes on, the wave is getting bigger and bigger and bigger, and when the radius is 2 meters, the area is increasing at that time at a rate of 9.42 meters per second squared. And even though this is a simple looking problem, every other problem will be tackled in the same way. Visualize the picture, the situation, label the variables, write down what you know, what you want using derivatives, find the relation involving the variables that you know something about and the ones that you are looking for. Once you have your relation, usually there will be functions of t, and so both sides are equal as functions. Differentiate both sides with respect to t, and then isolate for the rate of change you are trying to find. And that's basically it.